send you through tracks several files that we're going to work on it, all of us together, so you can follow me, you can do it. But
Oh my goodness.
let me to refresh your memory what we have done so far. Let me see if I can find the SPSS somewhere in here. How do I do that? Let's see. So you know what, while you are doing that, I might as well pass on.
Well, how was California, Dr. Kajal?
California was okay.
Okay.
It wasn't a pleasant thing, but yeah, it was annual commemoration of my brother's passing away, so I went there.
Oh.
So it wasn't a fun thing.
What part of California did you go to?
Went to Santa Ana or Irvine, Jenna.
The question and answer.
Danny,
Yes, sir.
Morgan.
Thank you.
Nicole. Did you guys cheat or anything?
Did I?
That's very strange that all of you got A plus.
Maybe you're just
Something
doing a
is
really
wrong
good
in
job
here.
as a teacher.
I'm sorry?
You're just doing a really good job.
Oh yeah, you're right. You're right. That might be the reason for it.
I can't even talk to you.
You guys
Otherwise, I
are.
would have
Oh, wait, this is Samira. That's why we got an A.
Oh, Zamira. That's.
Oh, I thought you said Danielle.
Oh, I said Danielle.
So.
Yeah, I said Danielle, but you know why?
She says right there, so.
Event.
Ooh, color. Ooh, fancy. Yours looks just.
Kelly.
Oh, nice.
Nora.
Oh, I have.
Sorry? I gave you two.
Probably because he had to give us so many answers through email.
I still have my 4.1.
John is not here. James.
Yes, sir.
Very good. Good job. Let me see. Matthew is not here.
Yeah, I'm not taking it.
Indra is not here. Zamira is not here. And
I just put it in the grade. Every time I go to California, I go to Porto's Bakery.
Okay.
Porto's Bakery.
where is that?
It's like like a famous Cuban bakery
It is.
by
Thank you
Burbank.
so much. I
Ah,
love it. That is the best bakery.
See?
Where-
The best bakery I've ever eaten in my life, and every time I go there, literally the line is out the door.
Yeah. Door. My
Yes.
friend was like three blocks away from there.
Everywhere I go, I ask, is it a Mexican bakery or not?
This
Those are
one's Cuban, but it's good. It's, yeah.
Yeah.
I always get boxes to take with me. Next time.
Yeah.
Let me tell you what my plan is for today. In fact, I have an ambitious plan for tonight. Hopefully I can finish.
Remember, you owe us like 45 minutes or 30
45
minutes?
seconds. Yeah, I remember I owe you guys something.
It
It's
was
not
like an
extra
hour and a
credit.
half, I'm pretty sure.
So I have to lower my ambition then. Did you all have any problem doing the one faculty test?
Is that the whole, yeah, I think we should go over the whole thing.
Yes, I have problems with all of them.
Because I'm not sure what I messed up with.
Okay, in that case, why don't I
Wait, I don't know.
go over one of them
Yeah,
and interpret it. How about that? Let me create a new file, new data.
See, my question
He
is,
gave
so
us 45
in the email you sent me, it was kind of confusing when you said if it's a one-tailed test, we divide the sig two-tail. Now, why, if it's one tail, isn't all of the 0 point, she tried to explain, I feel like you can't see it.
Yeah, let me explain for you.
Okay.
Probably better. So how do I open a new file? I just did.
New data.
Open, you have to go down to open, maybe,
Just go across the data.
I'm sorry? Correct?
Yeah.
I just did. Oh, here it comes. I did it. Oh, funny.
Teaching him, look at that, you're doing
No wonder I have
amazing.
opened several.
I-
This one didn't
I can
show
open a
up.
file, I can't do anything else, but.
Yeah. Okay, why don't we do one or a couple of them and then hopefully, let's do the rat one, huh? Or whichever, you
I
choose
think we
one.
should do 23.
So let's do 23. What is that about?
It's about the psychologist that trying to conclude if depression for elderly people is significantly different from depression in the general population.
Okay, read me the numbers.
The numbers are, 40? No, what do you mean?
Yeah.
Oh, hold on, I have to open it up, I was looking at things.
37.
Let me see, while you are looking for that, let me give
Can you also
Indras.
tell us about like how to format the null hypothesis that we're supposed to learn to?
Yeah, let me see.
You're just giving me things, the hypothesis.
So read the problem for me, I cannot remember.
The problem is, a psychologist would like to determine whether there is a relationship between depression and aging. It is known that the general population averages a mu, I think that's what it's
Oh,
called.
yeah,
Of 40 on a standardized depression test. The psychologist obtains a sample of 9 individuals who are all more than 70 years old. The depression scores from this sample are as follows:
Okay,
37,
37,
50,
50,
43,
what's that, 43, huh?
41, 39, 45, 49, 44, and 48. On the basis of the sample, can the psychologist conclude that depression for elderly people is significantly different from depression in the general population? Use a two-tailed test at the 0.05 level of significance.
So we're gonna do a two-tail and one-tail. This is depression, so make sure that when you do your homework, do me a favor, name your variable, so when I get your output, I know what's going on. So, our hypothesis here is that older people are more depressed than, let's say, national average. That's the hypothesis. A null hypothesis is that no older people are, they have the same level of depression as others, correct?
Yes.
So we collected, obviously we never picked up a sample of 9, it's not going to work.
Yes.
We, the whole idea, all of these homework that you are going to get, of course, the author of the book wants you to do it by hand. That's why they give you only a few samples. Anyway, we picked up 9 people, we measured the level of depression, and here is for each one of them. This is our raw data. We went to analyze, compare means, one sample t-test. We bring the variable from left to right, and down in here we put the number that comes from our null hypothesis,
It is.
which is 40.
Yes.
That's it. Click OK. You get 2 tables, and you need to print both of them. And I went over your computer test. For computer tests and your homework, don't put all of any of this garbage in here. Just simply print the appropriate tables and put them on a Word file, print it and give it back. I know that some of you with your computer tests, you killed many trees. So here is our descriptive statistics. There are 9 people in our sample. Actually, I brought something here.
It's a laser pointer.
Yeah. So there are 9 people in our sample. The average depression level is 44. Assuming that the higher the number is, the more depressed they are. I think that's what it is. So these older people, the depression level is 44, whereas the national average is 40. We want to make a judgment over this 4-point difference. And by the way, that 4 is right here. X bar minus mu. Remember the numerator of the t-test? X bar minus mu is 4. We basically want to make a judgment over this 4 point right here. And to see whether it's significant or you just got it by chance. We look at this number on the SIG and make a judgment. If you are making a two-tail test, automatically SPSS always give you two-tail test. If you are doing a two-tail test, you just compare this number with the alpha that you have in your mind.
So that's my question, if it's a two-tailed test, I was under the assumption that the .050 was broken into two and half was on one side, so it would be .025, and that means that that number's more, so we would fail to reject.
Very good.
Oh, so I'm right,
You're wrong.
I'm wrong.
But the way you were thinking was correct, because
Okay.
you were thinking of that curve, which is a good way of thinking. So I'll explain for you. This number also is
Split into.
it adds up the two extremes. So I'll explain for you in just a second on a curve. You'll see that I like the way that you were thinking. You were in right direction thinking. So I'll explain for you in just a second. But in real life, you look at this number is less than your alpha, let's assuming your alpha is 5%. If this is less than your alpha, you reject. So two-tail, this is less than alpha, you reject the null hypothesis, and we know that this difference in here, this 4-point difference, is significant, it's not by chance. And then when you want to write the conclusion, notice that older people are more depressed than national average, and that's the one that you need to show that it is more, it's not less. So when you write a conclusion, you need to write it in the layman's terms, so that older people are significantly more depressed than, say, national average. That's how you write. Notice the way I said it. A, I did not say reject or fail to reject. That's a no-no. You never said that in your conclusion. B, I do not know whether I put it in my list or not. If not, I'm going to put it. Always write your conclusion in present tense. Do not say will be or it was.
You wrote
No.
it in there.
I don't have it in there because I had in my mind to put it in there. So write it in present tense. 3, did you notice that I plugged in the word significant? 4, did you notice that I did not mention my sample? Nobody cares about sample.
Yeah, but I have a question about that. So for one of the questions, I think it's 24 or 25, it was the last one, it's kind of, hold on, I'm trying to go get here. Because we're testing, so if the data concludes that people in a sample are significantly satisfied with their lives than the general population.
Yeah, remember that nobody cares about your sample. The wording is not good. Yeah, it's misleading. Nobody cares about your sample. You take your conclusion to FDA and wants to get a patent or you want to get approval. FDA doesn't care about your sample is this or that. So that is this medication is helpful in lowering the cholesterol of people all over the world, yes or no?
Yeah.
So your conclusion should not make reference to the sample, but rather your conclusion, you want to make a general statement about this drug is effective or not. Whether this, whether older people in America are more depressed or not. This is the conclusion that you want to write. Don't make reference to your sample. Go ahead, I'm sorry.
Sorry. So when, from last class, when do we look at the two-tailed, the 029, and when do we have to look up T in the book and compare it to that?
No, you don't, no, that's the whole idea. When you do it on computer, computer does everything for you. You don't want to go to the table in the book, and those are all when you were doing it by hand.
Okay.
So, but that is a good question that really you do not care about this T and any of these things. Don't care about them. It is this one that you care. Why you don't care about these things? because computer has to, first it has to find the mean, and then subtract it from this in its memory. It has to do that formula. Find the standard deviation, find the standard error, divide them, and then get the t. When computer computes the t, it goes into a table inside the computer. It reads the tails in the normal curve, and then it gives you this. All of these things are done in order to come to this point. So all of the work is done for you. This had to be computed in order to find this one. So really you don't care about this. If you report them, of course, here, I'll show you tonight that you do need to report them. But this is the bottom, this is the gist of all these computations. It boils down to here.
I have one more question. So whenever you're writing the conclusion and after you write, like, evidence shows that they're significantly more depressed, and you put the comma, is the Z-score 40, would Z-score be 40 on this, or would Z-score be the mean? Because I noticed in the book, under conclusions, it has, like, the written conclusion and then comma, it says Z equals
Yes,
blah, blah, blah.
that's what I'm going to cover tonight. So, let me get ahead of myself. There are more things that we're going to add to this conclusion that you have written. Two things actually we need to add in here. One is that there is the issue of estimation that I'm going to cover tonight. And another thing is that you write your conclusion in a simple way that a layperson can understand. And then at the end, you want to write your conclusion symbolically. So those people who have taken this course and they know statistics, they look at that symbolic conclusion and they can understand what you have done and gives them more information. For lay people, you say the words, clear nicely. But for people who do know statistics, you want to write it symbolically. So in this class, after you have written your conclusion in words, you want to write it symbolically. I'm going to show you why you need to write it and how to write it symbolically. Now, one thing I didn't tell you guys, when you actually write your report, whether you're publishing or you're writing a report for your boss or whatever, none of these things will appear. None of these two tables appear in there. Occupies too much space. You do not show these things. What you want to show is that small symbolic conclusion. That little quarter of a line or 1/8 of a line that symbolic appears. So that's why you do need to learn how to write it symbolically. You want to write the gist of these things. See that a lot of garbage in here. You don't want to occupy too much space. I'm sorry, Eva.
Are we always going to do the 95 confidence interval?
That's what I'm going to cover tonight.
Okay.
Computer automatically will do this section for you, but no, you can change
Because
this.
if we change it, then
Yeah, you can
the
change it.
value will mean something different, right?
Yeah.
Okay.
I haven't talked about these three numbers, which I said I have a very ambitious thing. That's one of those things I'm going to cover. But going back, start from scratch, mechanically doing it is not that difficult. So if you're going to do independent two-tail test, you simply compare this with your alpha. If you were going to do a one sample t-test, all you need to do is to divide this number on the significant two-tail, divide this in half, and then compare it with the alpha that you have in mind. The question that Nicole is raising is that why? It just doesn't make sense, huh? So let's talk about this. If you are going to do two-tail test, and let's suppose our alpha is 5%, just for the time being. If our alpha is 5%, you put half of it in this tail, that's 2.5% in here. And then you put half of it in here, and then you want to make a judgment. So, we did this test in here. Computer went over that equation. Actually, it did the same thing that we learned. X bar minus mu divided by estimated standard error in t-test. This X bar is 44, this mu is 40, this estimated standard error is right there, standard error mean 1.5. You plug in all of those numbers in here, you get 2.667, this number right here. Okay? So what computer did to make life easy for us, because we always do independent, two-tailed test. It got this 2.66. It located in here, it's on this side, it's positive, right? 2.667 in here. Let's say this is right here. The T mode is right here. It computed this area. It found its symmetrical, I don't know, the mirror image of it on this side, that might be a good word. Mirror image of it in here, negative 2.667. So it found it 2 times. One time for that tail, one time for this tail, and computed this area. And then added up these 2 mirror images, added them up, is this. So you see that this part, the 2.26, it is within this tail. If you were going to do one tail test, all you're interested in this blue part. You don't care about this part. You're interested in this one. If you put all of your 5% in here, this is all 5%. Well, this is within 5%.
Yeah, but I guess I don't understand. Maybe I'm just really bad at math. I thought 2.6 is bigger than 2.5, so wouldn't that be on the inside?
Oh, this number?
Yeah.
Oh, wait a minute. No, this 2.5 is the percentage. That is the t-value. This is this point right here on this line. That is not a percentage.
So
That's a t-value. It's like a z. This is a z-value. It's not a percentage. You find this z-value, go to the table in order to find the area. So this is the number of wooden blocks in that tail, right there. How many wooden blocks are stacked up in here? Whereas this 2.5 says from this point on, you have 2.5 blocks on this side. Well, excuse me, 2.5. I'm confused. I do not know how much this is. This is half of that.
Okay.
This area is 0.0145. About 1.5 wooden blocks. From this point being 2.67, from this point on, there is 1.5, less than, yeah, 1.5 wooden blocks in here. So if you're going to do a two-tailed test, which you will do a two-tailed test always, this number is this t plus its mirror image. Or in other words, you double this. You double this. Did I say something bad or nasty? You are wrong. It could be that one. No, the computer.
It's tiring.
Very, very strange, huh? But, oh. So this number actually is double of this. I can see why the confusion comes into picture. But you always look at this and compare it with your alpha, if you're going to get it. If for whatever reason you want to do one tail test that you in real life you should not do that. You divide this in half because you're only interested in this part. And then compare it with your alpha.
When we do a one-tail test, do we have to state that in our conclusion?
When you do one, if you do a two-tail test, don't say anything. There's no need to say two-tail. But if you do a one-tail test, you need to say it.
No, you wouldn't state in the write-up, just afterwards in that little,
Yeah, and after you write it symbolically, but why is it that you want to say it?
to know the measurement.
Because if you put all of your alpha in here, you have a larger area, correct? If you put all of the 5% in this A, you have a larger area of rejections or larger rejections of, it makes it a lot easier to reject and tell the world that you have found something. That's why you need to tell your reader that, look, this is not the standard thing to do. Because you have expanded this area, the chance of you coming up with Eureka is much higher now. With all of 5% in here. So, if you're going to publish, you don't want to do that. You don't want to do one tail test. If you take the other course, the C part of this course, there's a set of articles that we're going to read on Milwaukee voucher program, several articles, 3 articles. Somebody came and said that, no, this voucher program does not work with statistical analysis. Another person came and made argument that the first one was wrong and this and that. And then the third person came. He did a statistical analysis, did all analysis, he came out with the fact that yes, it worked, it was wonderful. But when we looked at the data, I said, wait a minute, this guy is cheating. First of all, he's using alpha of 10%. And he put all 10% in here, like this, and then one take, obviously you find results. We're all, the guy is from some high caliber university, I think University of North Carolina, Chapel Hill or something. That doesn't make sense. The guy is from this university and you need to take a statistic 101, you know, that you don't do that. You don't, first of all, you don't use alpha of 10%, unheard of. Second is that you don't put them all on one take. Because you make it, this area is so large that it is, make it a lot easier to reject the null hypothesis and say, yes, it works. So in the classroom, the first time, we said, you know, let's look up this guy. So we looked him up. And we read about him. The guy is, he has one of those think tanks on education, whatever. And he got a huge grant from one of these very conservative institutions, whatever, to prove that this voucher program in Milwaukee worked. He did all the statistics. He realized that, no, it didn't work. But then he had already received a lot of money, grants from a think tank or from a very conservative, so he massaged things. So yeah, that's why you never do one tail test. This guy did because he received a lot of money. They use alpha of 10%. At most your alpha is 5%. I'm sorry, did you have, Mike, did you have a?
No.
Some, did you, Nora, did you raise your hand? I thought somebody raised.
I was stretching, so.
Oh,
That-
stretching,
that was probably
okay.
it. Sorry.
Anyway, is that clear? Shall we do another one or should we move on to the? Sanke?
Yeah.
But do ask, all of these questions are very good. I'm glad that you were thinking in terms of this. Okay, what, if you remember toward the end last week, or 2 weeks ago actually, we started a new t-test. There are 3 t-tests, there are 3 versions of t-test. This is one sample t-test. There are 2 other ones that are by far more important and more popular. This one, I would say, of all the t-tests that I have done for my reports, for publication, I would say less than 5% of them is like this, one sample t-test. I would say 95 or probably more are the other 2 that I'm going to cover, especially the second one I'm going to cover. There are times that you want to compare 2 populations. Let's say you want to compare some aspect of women and men in America, or one medication versus another medication, one fertilizer with another fertilizer, one method of teaching versus another method of teaching. So when you're comparing 2 populations, you use independent t-test. Independent t-test, or independent samples t-test, or 2 samples t-test, either one. Usually, most people independent t-test is understood. And if you remember, graphically, I want to keep those things because I may make reference to it. Here you have, let's say, imagine a population of men in America, and here is the population of women in America, and you want to know whether the population of men and women, let's say, in the number of words that they have, is different. So obviously, there's no way they can test everybody in here. You pick up a sample in here, as large as you can get, a sample from here, and then let's say you pick up 100 men randomly, and you check to see how many words they have in their brain. We came up with, I can't remember last time I used this number. Then you get a sample of you, put some stick on it. You get a sample of women, and hook them up to wire them up with a computer, extract from their brain how many words they have, and here is the average, let's say. Our hypothesis, let's say our hypothesis in here is that women in America have more words than men. That is our hypothesis. And our normal hypothesis is that there is no difference in the number of words that men and women have in America. They're the same. So we want to know whether these 2 populations are different in terms of number of words that they have. So we picked up 2 samples, here are the averages, and when we look at the difference, there is a difference of 1 word, and common sense tells us that 1 word difference, we are not going to run barefooted in the streets and say, Eureka, Eureka, I found it. 1 word is a sampling. After all, if you pick up another sample of women, you end up with a different number, same thing in here. But if the difference is 2, again, no, it's not that, it's not significant. 3 words difference, no. But if you look at the difference and it's, let's say 70,000 in here, you have a sample of women, they have, on average, have 70,000 words, you have a sample of men, 30,000 words. The difference is 40,000 words. Come on, this could not have been by error. This is not a sampling error. If these 2 are so different, most probably these 2 populations are different. from a big difference down in here, we arrive to the conclusion that there is a big difference between the two populations. But the point is that where do you draw the line? How large this difference should be for you to decide that the two populations are different? 10 words, 15 words, 1,000 words, where? Don't worry, t-test will do the job for you. It is t-test that will tell you whether this difference is significant or not. By significant, I mean that you didn't get it by chance. It is real. It exists in here. We do t-test, and it is the same equation. Except in here, we want to look at the difference between these two. Is there a difference between x bar 1, let me put x bar 1 and 2, whatever, male, female. X bar 1 and x bar 2. Is this difference significant or not? The two. Down in here, you want to put a cumulative standard error. Forget about the equation. If you're really interested, read the chapter. It tells you how to compute it. In this case would be, let's say, x bar 1 minus x bar 2, standard error of the difference. It's the same equation. So computer will find the t for you, puts it in here for you. Let's say it comes up to this. Find its mirror image in here, add them up, put them in here for you, and you proceed. So we're not going to go through equation anymore. Forget about equations for now. But it's the same thing basically. Computations become, really the computations is a little bit convoluted. How to compute, it's not that convoluted actually. How to compute this part, put it down in here, find the t, and if you are going to do it by hand, you go to the book, go to the t table, with the t of, let's say 2.66 if this is it, read it and then proceed. So let's do a couple of them. I'm going to, as a matter of fact, I have sent you, download them on your desktop. Now I cannot remember which one I have sent.
You did self-esteem, gas, words, and
Self-esteem and what?
independent. Self-esteem, gas, words, and independent t-test. I'm guessing that's what it stands for.
Okay. So we had this one, independent t-test.
Yes.
Okay, open it because that's a good one because we can do several of them in here. So when you want to do independent t-test, I cannot remember whether I have mentioned or not. T-test in general, all three of them, is that you're comparing two things. Not three things, two things. For example, in this example I put on the board for you, you want to compare men and women, or this drug versus another drug. You cannot compare 3 drugs or 4 drugs.
Why?
Because t-test doesn't lend itself to that. There's another statistics that I'm going to cover next week. That's called analysis of variance. That is when you have several groups that you want to compare. Imagine I want to know whether is there a difference in the number of vocabulary of black, white, Hispanics, and others, for example. Several groups. But t-test is always for 2 groups, like male, female. So what is important for you to notice is that you always have one variable that contains all of your variables. I mean, all of your the categorical variable. In the example I put on the board is that in one column you put male, female, male, female, male, female, and in the other column you put all of your scores. So the way that it should appear in SPSS or even Excel, if it appears that way. In one column you have your categorical variable, male, female, or drug 1, drug 2, or method 1, method 2, or management 1, management 2. In the second column you have your scores.
This
So
is,
in here, go ahead.
this is only for independent though, this isn't needed for,
Basically, always the way that you enter data into Excel or SPSS will look like this. Yeah, even if you're going to do the other one I'm going to teach. So in this example, and here there are several examples I want to go over them. We want to know whether people who have personality A and personality B are different with regard to amount of money that they make, with their blood pressure, their happiness in life. Several things we want to compare with regard to people who have A personality. These are people who are go-getter, tense, and very active in life. Personality B, lay back, relax, enjoy life. That's personality B. So our first example is that, let's say, as you all know, let's say, no, let's the first example, let's put it with income. We want to know whether people who have personality A are more successful in life in terms of money. They make more money than people who have personality B. So we went out, caught a bunch of people, some of them are personality A, some of them personality B, asking that, how much money did you make last year? Notice that when you do independent tests, there are two variables that you are interested in. In this case would be type of personality and income. In the example I put on the board is that gender and number of words. So there are two variables that you're working with, two columns that you're working with. So my hypothesis is that people who have type A personality make more money than people who have personality B. That's my hypothesis. My null hypothesis is that there is no difference in the income of people who have personality A and personality B. So no difference. So here is the variable that contains my categorical variable, and here is a variable that contains my income. We are going to do several of these independent studies, 3 of them, right, or 4 of them here. And I'll explain it in this. I will explain it incompletely, and then we'll come back to every one of them, and then I'll explain it completely. The reason is that I don't want you to get confused, so I'm going to raise the heat gradually. So we go to analyze, compare means, independent sample speakers. The variable that has your scores, you bring it from left to right, in this case with the income, you bring it up in here. The variable that has your grouping, in that case will be personality type, bring it down in here. And here is the twist, if you remember. There are times that, there are times that,
Is it behind you on the board?
oh, here it is. There are times that in this column, you'll have several groups, and you want to compare 2 of them. Let's say you have black, white, Hispanic, and others, and you just want to compare blacks and Hispanics. So computer asks you which 2 groups do you want to compare in here. So you have to tell computer. I cannot remember how I have coded it. Let me right click in here as a reminder. Oh, I coded them 1 and 2. Okay. So anyway, the 2 groups are coded 1 and 2. Define groups, and in here you say group 1 and group 2, depending how you have coded it. Continue. Yeah, that was the only twist. You're ready to go. Click OK.
And you have to do that even if you just have the two variables, right?
Yeah, I do not like about that. It seems to me that the SPSS syntax underneath should have been written in such a way that computer should have recognized that in this column there are only two categories. But anyway, you have to do it. Yeah, it's an extra step. So you get two tables. The first one is your descriptive statistics, and the second one is your inferential statistics. And here, remember when you do your homework, I want both tables. Although in real life, you do not show any of these tables. You show it symbolically. So anyway, we have the name of our variable that has scores is annual income. We're comparing the annual income of people with type A personality and type B personality. So here are the sample sizes 50-50, and here is the average income of each group. On average, people who have personality A make $77,000, people who have personality B make about $38,000. We want to know whether this difference is significant or not, or it is by chance. So this is X bar 1, this is X bar 2, it's a numerator of this. So we want to make a judgment over this difference. By the way, that difference is somewhere in here. Here it is, about $39,000 difference. So we want to make whether this is different or not, significant. You go to SIG 2K, look at this number. Is this less than 5%? Assuming that yes, we reject the null hypothesis, and we conclude that yeah, these two numbers are significantly different. And notice that personality A is more than this one. That's the direction of the difference. So our conclusion, the way that you're going to write it is that people with personality A make significantly more money than people with personality B. Carlos.
If your categories have different sample sizes, is it possible that your significance will be different between the two categories?
Let me put it this way, that it would be very rare for you to come up with exactly the same sample size. That's usually not the case. Here, I have exaggerated. So you should know that the sample sizes are not necessarily the same. But you are right, you know, all these computations have to do with the sample size. Ideally, you have a large sample size so that that difference doesn't make cause any problem. If your sample sizes are very different, you have 600 people in here, 25 in here, that may cause problem.
Okay.
So long as they are more or less close, you're okay.
Okay.
I'm sorry, go ahead.
So the numbers under the SIG 2, the SIG 2 tails, are they always going to be the same in those two?
That's what I want to talk about. That's why I gradually I want to raise the heat.
So which number right now, are we looking at the top or bottom?
Just for the, yeah, for the time being, let's look at the top one.
Okay.
But sometimes you want to look at this one. Why? And how do you decide whether to go to top or bottom? But we'll get to that in, I promise, in 4 minutes. Okay, let's do another one. I want to know whether, let's look at that. I want to know whether, now that we know personality A people are more successful in life, success always in life means money, correct? Now that personality A are more successful in life, how about their blood pressure? How about their health? So we go to analyze, compare means, independent t-test, put blood pressure in here. This part is okay. Click OK. So personality A people have blood pressure of 124. Personality B, they have personality 79. The difference is significant. So type B people are, when it comes to blood pressure, they are doing a lot better, huh? They are much, much healthier. Shall we do another one? This time let's do a shortcut. Why don't you just go in here, independent, short. You know what? We have been doing these things 3-4 times. This is a waste of too many clicks in here. I want with one shot, forget about everything that we have done in here. In one shot, I want to get income, I want to get blood pressure, I want to get whether they're satisfied in life. In one shot, I want to get all of them. So I bring annual in here, blood pressure in here, satisfaction in here,
So if
frustrated are in here.
satisfaction's not a number, that's okay?
But that's an interval. I have it on a scale of 1 to 5. It's a Likert scale. Remember interval scales. Likert scales. 1 to 5, 1 to 7, 1 to 11. The Likert scale. Because they are interval, you can treat them like ratio. Always interval and ratio are treated the same. So notice that in here I have put all of them in here because I want to compare personality A, personality B in here. So instead of doing it one by one, here is one shot bang. Here they are.
And they're all significant.
Except it has put them nicely in one table, and here they are. So on blood pressure, we rejected the null hypothesis. Level of satisfaction, we reject. Frustration, reject. All of them are reject. Level of satisfaction. Remember, 1 would be miserable, 5 is very happy in life. You see that personality B are much, much happier in life than the other one. We know that it's significant. How frustrated they are in life. Personality A's are much more frustrated than the other one. So the point was that we can do a lot of t-tests in one shot fast instead of one by one. Okay, let's go back in here, the things that I want to show.
Dr. Tawanda,
Yes,
what's the other significant value, the first one?
that's what I want to talk about.
Okay.
When you do independent t-tests, there is a twist to it. And the same thing with the one that we're going to cover next week, ANOVA. If you are going to do this equation, the standard one, the assumption is that the two groups that you're comparing, let's say men and women in America, number of words that they have. You can use this equation only if you can make the assumption that these two populations have the same shape. If you draw the bar charts, somehow they look the same. That's the only way that you can use this equation. How in the world can you tell this 150 million men, 150 million men, the number of words if you draw their distribution that look like the same? Do not know. What computer will do for you is that must be done. The computer will pick up the two samples that you have, 50 men and 50% A, 50% B. Pick up these two samples, looks at their distribution, and runs a test called Levine test of homogeneity of variance. It's a nice word if you want to impress your boyfriend or wife or girlfriend. Levine test of homogeneity of variances. It runs a test based on the two samples. and tell you whether based on these two samples you can make the assumption that these two populations have similar shape or not. And that test is right in here. Levine test of homogeneous variances. It runs a test for you. It finds the significance of it. If it is not significant, that means that, okay, yeah, based on these two samples, they are not different. The shapes are the same. If this is more than 5%, always use 5%. This is a standard. Always use 5%. If this number is 5% or more, that means that, yeah, based on these two samples that you have, you can assume that the two populations have the same shape. If that is the case, you go to the top row and look at everything in the top row. However, if this number is significant, less than 5%, like this one, that means that you cannot make the assumption that these two populations are the same. Men and women in the US have similar shape. You cannot make the assumption. You cannot use this equation. There is another mumbo jumbo convoluted equation, mathematical equation that need to be used in order to compute this second law. So computer automatically uses those equations that we are not covering and compute everything. So you get the results anyway. Bottom line, let me finish the bottom line, see that how simple it is. When you do independent t-test, I don't know, where do I put that? When you do your independent t-test, the first thing you want to look at is this significance of your Levine test. And look at my finger. If that number, 0.003 right now, if that number is more than 5%, you go to the top row. If that number is less than 5%, you go bottom row.
When you mean top and bottom, you just mean on this exact same chart.
If this number is less than 5%, like right now, then you go in here to this line.
So less is bottom.
If this number is larger than 5%, you go to the top row.
Oh, because we're gonna use all those other boxes eventually, we're just not using them.
Yeah, we are, well, actually, we just use this for, let me see. We use this box and these two boxes in a few minutes.
So in cases that it is above or below or whatever,
Like
is the SIG two-tailed ever, does it ever differ?
No. Oh yes, these two are not necessarily the same. I have fabricated, I have exaggerated, came out the same. But these two numbers are not necessarily the same. So,
Dr. Kajal,
yes,
when you're saying, so for instance, this one is less than 5%, we're looking at the bottom row.
yeah.
What are we looking at the bottom row for?
So disregard this top row completely as if it does not exist.
Okay, so for 80.
This is
Okay.
the t-value that you compute through that nonsensical equation. This is your level of significance. This is the real thing, really. This is the one that you're interested in. This part basically is a clue to tell you go to the top or go to the bottom. And when you go to the bottom of a row, you want to look at this number to reject or fail to reject. That's the twist. And it will become a second nature for you that you very quickly, you know that on this one, oh, I'll go to the bottom row. Let's see what else we're doing here. This is one of them. How about this one? This one is
Bottom.
blood pressure. Go to the top or bottom?
Top.
We go to the top row. Disregard as if the bottom row does not exist. This is about 86%.
Oh, you look at the significance, not the F?
No, forget. Computer has to compute the F, this point. It has to compute this point in order to find how many wooden blocks are in here.
So yeah.
And don't say why F, what not T, because there are many tests. We're just learning the T test. Levine does an F test for you, but that's another issue. All you need to do is use this as a clue to go up or bottom. Let's go to the next one. Let's go to level of satisfaction. Top or bottom?
Tom,
Top. Let's go to frustration level.
Bottom.
Wait,
Is it
oh,
less
shoot.
than
No, no,
5%?
yeah,
Go
sorry,
bottom.
yeah, bottom. I was looking at 14.7.
And I hope probably I have misled you in here that I have all zeros, but they don't have to necessarily be the same.
I like it like this, you can keep it all zero.
Yeah. Okay, that is independent t-test, guys.
So
It's
the
nothing
F,
in it.
the F calculates for the two variables, the tail.
I'm saying again,
The F calculates the tail for the two variables. And then the significance level tells you how, you know what I'm gonna think about it? Okay.
don't think about it right now.
Alright.
Because when you do a t-test, we are using a normal distribution. When you're going to do a f-test, I'm going to confuse you guys.
Yeah.
But when you do f-test, it's like this. It start from 0 on. It is one tail.
Are we doing F tests throughout this class?
Yeah. Yeah, we do two. Then we'll do one that is f-test, looks like this. We do another test, chi-square also looks like this. So not all bar charts that you draw will come out this way, but some of them, anyway, I don't want to confuse you. But Levine test is not a t-test, it's something else. All you are interested is to use this number, significance of Levine test, as a clue to go to the top row or the bottom row.
So the final conclusion will be on the two-tailed value. We're just using the Levine's value.
Yeah, Levine is just a clue. That's
Okay.
the real thing is this one, this column. This significance is the one that helps you to reject or fail to reject the null hypothesis. Is the drug effective or not effective? Yes.
So will there be an instance where the significance of the two-tailed based on the equal variances will be different from each other?
These
And
two.
so, yeah, so if you accidentally look at the equal variances assumed instead of the equal variances not assumed, and they have two different values and significance, you could mess up your conclusion.
That's right.
Okay.
Very often these two numbers, let me get to another one that is clear. Often these two numbers are different. And in one of them might be reject, and the other one fail to reject. So you need to be aware which one to pick and interpret. So it is going to make a difference, huh? And one of them you might say that yes, the drug is effective, and the other, if you look at the other one, they said the drug is not effective. But you have, based on this number, you decide, aha, I'll go with this one.
Does the data automatically account for like the relationship between variables or variances that are not assumed? In other words, like if you use equal variances not assumed, would that create an issue with the quality of your findings?
No. The quality is the same.
Same.
One other thing, yeah, no, it's the same. The mathematics of it is correct. It's that except you don't use this math, you use a different math.
We don't use it.
That's why you want to use computer. You don't want to do this in real life. Even with a assumed one, you don't do like the sample size is very large. One other thing that I did not cover last time, I think I did not. Notice that when you do independent t-test, you're dealing with two different populations, correct? With two samples in here. Computer needs to compute the standard error of this one and then a standard error of this one, combine them, and then put it in the denominator. So when it tries to compute the standard error in here, it uses degrees of freedom of, for men, n minus 1 of men. In here, it uses degrees of freedom of women, n minus 1 of women. And when you combine them together, put them down in here, you have the total n. So your degrees of freedom would be the total n, n of men plus n of women, let's put a cap also, minus 2. So, when you do a, and this is another thing that will become confusing. When you do a, I can see it, let me scroll that up a little bit. So your degrees of freedom, if you are going to use this equation, assuming the things are, shapes or variances are the same, is always total n minus 2, not minus 1, 2, because we are dealing with 2 samples. So notice that in here, yes. Let's see if I can pull this up a little bit. Notice that it is, we have 50 type A, 50 type B, that's 100 minus 2 is in here.
But why do we take the 2 away?
Because there are 2 samples, each of them is n minus 1, n minus 1. Combined would be n men plus n women, that's 100, minus 2. Now, that degrees of freedom for if you are doing an equal variances, assume is that if you go to that convoluted mathematical equation, you end up with a number that is so weird. Look at this. If you're going to put a bottom line, look at the degrees of freedom, it has decimal. Because the computation is so convoluted and messy. We're not going to compute it by hand. Forget about it. Oh, just, if you're on the top, it's very easy to recognize that there are 100 people in our experiment, and we're comparing 2 groups or 2 samples. So it will be total number of individuals in our experiment minus 2. That's everything about independent t-tests that I wanted to tell you. The twist is to go to the top or bottom. Degrees of freedom is n minus 2 if you go to the top row. To the bottom row, just look at that number. Forget about how to compute. Actually, I cannot remember how to compute it myself.
So would the DF be the z-score?
Degrees of freedom?
Yeah, what would the z be?
Degrees of freedom is always that is sample size minus 1.
So where up there would we find the z-score?
Z, we got away
Oh,
with the Z.
it's not on here though.
No more Z.
Well, then whenever it comes to writing the conclusion, why do we have to put z in the conclusion? In the
Never
book,
put Z in your conclusion.
but in the book it has that, that's why.
Oh, that's because you did a Z test. You are moving to T test. So you don't put Z, you put T. So the next thing I want to tell you might actually answer that question. You write your conclusion. Let's say for this one is on, what is it? On blood pressure, correct? We conclude, and we go to the bottom,
No, we do the top.
this one, to the lower row.
I thought we went to the, am I blind? I thought we went to the top. No, to the bottom?
So here is the significance of, oh, excuse me, you are right.
Oh.
Here's the significance of the, here's the significance of Levine. We go to the top row, we look at this number, it is less than 5%. we reject the null hypothesis. So blood pressure of people with type A and type B are significant. Let me pull this down. It seems to me. I want to use the board in a minute. So we know that the blood pressures are significantly different. So we go up in here, we look at the blood pressures. People with personality A have significantly higher blood pressure than people with personality B. Correct? In real life, whether you are writing a report or a publication, these tables do not appear. What appears is you're writing simply what the conclusion is, and then you write it symbolic. Symbolic, whether you are doing one sample t-test, independent t-test, the next one pair t-test I'm going to cover in a minute. The symbolic of it is exactly identical. Here we have done a t-test, correct? You put t, that means we have done a t-test. If you did a z-test, you put z.
I was putting Z everywhere, so my homework says Z.
Yeah, but here we are doing t-test. In the parentheses, you put the degrees of freedom. In this case, would be 98, huh? Here it is. So the value of the t equal to the value of the t that you have found is, well, disregard the bottom row. We are looking at only the top row, 21.029. Correct?
Yeah.
So we have done a t-test with the degrees of freedom of 98, and the value of the t is 21.29. We put comma, and now the rest, this is easy. The rest is extremely important. You want to use this term to mean reject null hypothesis, and you want to use this term to mean fail to reject null hypothesis. Reject the null hypothesis, fail to reject the null hypothesis. So, we did a t-test, our degrees of freedom is 98, the value of the t is this, comma, p, that means this number, percentage. This percentage, we use it with p. Our p is less than, that means what? That number on the sig is less than the alpha that we have used for our criteria. Now remember, if you leave it as it is, that means that you are using two-tail test. If you are going to if you are using one-tail test, do mention in here that one-tail test.
Will we just put comma one tail?
No, just write one-tail test, no comma, nothing.
So the P is the sig number?
Yeah, the P makes reference to this number. I'm saying that this number is smaller than 5%. A person who knows the statistics knows, if this number is less than 5%, that means reject. If you reverse the sign and put it this way, that means that this number is larger than 5%. Which means what? You fail to reject.
I feel like we should stop while everyone understands.
Huh? Yeah. The only, see, those people who have taken statistics, they know a statistic, they can understand this conclusion. Oh, this guy did a t-test, this is sample size plus 2, of course, and got a value of t of this, and then he's rejecting the null hypothesis, the alpha hypothesis.
So we don't have to write the actual number, we just write P?
I think APA, which is different than all other ones, I have noticed that, or they have told me when I send it to a place to be published, they said, put the actual P in here, the number in here. But standard is this. Yvonne, what do you have in mind?
I was just wondering why they say that, but standard is the 0.05. Like, what are you going to grade us against the 0.05 or the 0.000?
Yeah, that means that this 0, 0, 0, which means P. We did a t-test statistic, the number on the sig, which is this, is less than 5%. Instead of having this, for this number we have put P. This P is less than 5%.
So we put the letter P, not the,
No, not this.
okay.
Are y'all with me? Was that easy? So I'm going to make it a little more convoluted. Guys, don't show this at all. Nobody will see this. And this occupies a lot of space for a journal. No way they are willing to print this. Also, you don't print this in, let's say, a report that you are writing. Imagine this does not appear in here. Just for a second, imagine. This doesn't appear. This appears in your conclusion. Are you with me up to here? I want to step back and talk about the meaning of this number, by the way. You have to know the meaning of this number that is in here. This number, you write that down actually. The number under significance two-pair test, this number represents the exact amount of type 1 error that you are committing when you reject the null hypothesis. What does that mean? That means that if you reject the null hypothesis, there is this much chance that you are wrong. This is the probability of you being wrong when you say that the drug is effective or there's a difference between A and B. There's this much chance. Actually, there is a number in here. I told you already. If you click on it, you will see the actual number. So when you reject the null hypothesis, you're probably wishing to see an extremely small number here. The smaller, the better. I'm saying that the drug A is better than drug B. My chance of being wrong is this much. Obviously, you want this number to be very small, huh? The smaller, the better it is. You're in a more solid ground. This is the amount of error that exists if you reject the null hypothesis. Is that clear? Because I want to twist that symbolic equation. If it is not clear, let me know. Has it sunk in the meaning of this? If you reject the null hypothesis, there is this much probability that you are wrong.
How do we find the percent of type 2 error?
You don't care about type 2, that's not important. Type 1 is important. You know, type 2 error is that say that, I haven't found anything, others should go and look for it, they might find something. But when you say that the drug is effective, let's put it in the market, you're playing with the lives of millions of people throughout the world. That's important. But if you say that, well, I don't know whether this drug is effective or not, we need to do more experiment on it. Okay, probably. But there is a way to find it, by the way. It's not that difficult.
I just watched a movie about that the other day. It was with Bruce Willis, and they were changing the samples, the results of, it was some drug for he was like a doctor. Nobody's seen it? Oh my god, I can't remember the name. I bought it on demand, but they were,
Is it a newer Bruce Willis?
wait, was it Bruce Willis? And they were trying to kill him or something, and he was, oh no, it's old, I lied, it was Fugitive, I think was the name of it. He got his wife got murdered, and they were trying to murder him. It's really old, Harrison Ford,
Oh,
Bruce
yeah.
Willis, John Wayne, I don't know.
Oh, I know that.
It wasn't new, I watched it,
Okay.
but
Yeah.
I thought it was new because I've never seen it. No, but they changed the samples and they tried to murder him because of it.
I have mentioned two things. One is that never report this. Keep that in mind. Everybody sees that. The second thing that I mentioned, because these two are go together in just a second. The second thing that I said was that this is the amount of type 1 error that you're committing. How much the probability that you are wrong. Correct? Now, forget about this. Nobody sees that. This is what they see, people. Let me read this for you and tell you what this means. We did a t-test, and the value of t-test is this much, and we are less than 5% chance that wrong in our judgment. This is what you're telling the world that. Less than 5% I am wrong. Look at this. What people do not see. You're in such a wonderful, solid ground. You're probably 1 in a million chance that you're wrong. You don't get credit for it, idiot. You're telling the world that, well, less than 5% might be wrong. You're not getting credit for such a wonderful results. That's probably, if you click on it, let me see. By the way, what is that number? Oops. Oh, here it is. Whoa, look at that. You see this 4? Put 37 zeros behind it. That's 1 in a zillion, even more than that. Chance that you are wrong. Very remote chance that you are wrong. You're not getting credit for it because nobody sees that. People see this one. So even though you use alpha 5% in your mind as a criterion to reject or fail to reject, when it comes to writing your result, don't put 0.05. Get some credit for it. Like in this example, I probably would put 0.001. I'm less than 1,000, 1 in 1,000 chance that I might be wrong. If you put 0.05, it's fine. Except you don't get credit for this course. And in real life, you want to get credit for your such a solid results. I did a t-test, the p-value is this. I am rejecting the null hypothesis. I'm saying that the drug is effective, and I might be 1 in 1,000 chance I might be wrong. That's a very small, remote chance. Everybody accepts. In other words, when you write your conclusion, I suggest you put one of these 3 numbers, which if you reject the null hypothesis, put one of these 3 numbers, whichever is the best, whichever is the smallest. Now, don't put 3 zeros, that's too pretentious. 1 in a million, maybe don't write that. So in this case, you see that it's extremely small. Probably this number is the best one to put in here. Now, did you all get the point? You could have put 5%, but then you don't get credit. That's probably the best word I can use. Let me see if I go down in here. Let me see. Well, all of them I came up with 0, 0. So.
Dr. Kugama, is that
Well, in this particular case, yes, it all came out 0. But if, let's say you end up with a bottom row and this is a different number, of course, this is the number that you use as a criteria, as if top row does not exist. And if you reject the null hypothesis, if this is less than 5%, you decide whether to put this one or this one or this one, whichever fits best. Please.
So on one of them where we're supposed to use the bottom row, but it has that crazy DF,
Yeah.
do we still write 98 or do we still have to write 87 or 67 points?
Put that crazy number. I personally, at least one occasion, I felt that people will not understand. Even educated people sometimes do not understand. I have put it top row, but I knew that I was cheating and I was wrong. But for this class, just go ahead and put this number in here. Yeah. I'm not sure.
Even when you know you only have 2 samples, why is it not 98 no matter which row? Because you only had 2 samples you're comparing, so why does it even come up with that crazy number?
Why it didn't come out with 98 in here?
Yeah.
Because there's some convoluted mathematics that is used, because the two populations are not, they do not
Okay,
have the
that goes
same
back
shape.
to
Some convoluted, I knew how to do it, I used to teach them. I have even forgotten how to compute that. You come up with this ugly number that I bet you a lot of people start looking at them, how did you come up with this number with decimal? But yeah, for this class, just put that number in the parentheses. I will understand, and other people outside may not. You know what, guys? Why don't you all do a couple of those independent t-tests so I can come over your hand and see what you have done. So what do we have? We have one that is the one that I sent you. Words. Self-esteem. Why don't you all do self-esteem? So the first one we want to do is that we got a grant and we opened that, I told you that we opened that Austin Learning Academy in East Austin. And federal government gave us a set of questions to ask. And then we ourselves came up with some questionnaire. One of them that it was ours, not the federal government, we decided to measure the self-esteem of students. So, and then it was a convoluted design. We picked up 2 groups of students, 10 to 13-year-old kids from East Austin. One group of students are experimental group. These are the ones that we kept them after school, we gave them a treatment. And then we had another group of students that were our control group. We didn't give them treatment. We just tested them. So imagine at the beginning of the year, September 1st, we invited both groups to come and we tested them, gave them I remember, we gave them Rosenberg self-esteem, 10 questions. The minimum number was 4, maximum is 40 for Rosenberg self-esteem. So we gave both groups the test. And here's the September 1st, beginning of the year. We wanted to establish the fact that these 2 groups that we have randomly picked up, experimental group and control group, they are the same at the base. The base is the same with regard to self-esteem. This is one of those rare occasions that we're praying to God that God please make sure that we do not reject the null hypothesis. We fail to reject. That means that they are probably the same. And we don't want to reject and say that yes, one group has from the very beginning has higher self-esteem than the other. That would have messed up our.
So your hypothesis is that they're the same, that there is no difference.
Yeah, our hypothesis was actually similar to our null hypothesis. Our hypothesis was that both experimental group and control group have the same level of self-esteem from the beginning, which really it was a null hypothesis to begin with. So we picked up, so that is what you want to do. In one column, we have experimental group, I put a program group, and the other group is control. Yes.
We're using the one sample t-test, right?
I'm sorry?
We're doing one sample?
No, independent t-test. You have two groups, control group, experimental group.
There's only before and after.
There's not a third column.
There's no,
You only need
There's not
there's not
categorical.
a third.
Let me see, which one did I send? Did I send you?
It's
It
team.
There's
just
no
says
category.
before and after.
Ah, I sent you for the next thing that I want to teach you. Forget about this one. I'm going to teach you the third t-test. The third is this. I'm afraid to confuse you guys.
I know, I think you should just let us.
But well, let me say it. Let me say it. We'll get it. As you will see that the other one I want to teach you is by far better than this one. There are flaws in this independent t-test, even though this is the most popular. There's a flaw in here that I want to bring to your attention. This third one that is called pair t-test. You get the same individual, you test him before and after to control for all extraneous elements. But anyway, I sent a wrong one, but hang on to it. We are going to work on it tonight, actually. What else do we have for independent t-test?
Gas.
Words.
I'm sorry, which one?
Words.
Words, that's 3
And
columns.
gas.
Words, yeah, why did you all do words? That's a male, female, am I correct?
Yes.
And what else do I have also in there?
Words and
Words and then an unlabeled variable.
That is the years of education. Yeah, that unlabeled one is years of education. Label it as years of education.
So is this kind of like what you did before class, on,
Yeah,
let's say my
we did that.
hypothesis?
Yeah, or words. Yeah, so use word and gender. What's the name of that file I sent you for self-esteem? Do you remember what the name was?
Just esteem,
The same as this
or
one?
self-esteem, sorry. Yeah, that's that one.
Let me open it, so I'm not going to send it twice for you guys.
This one looks like it doesn't have a space, but the one that we have has a space.
Let me just take a look at it.
Between the words.
This one has space in between, huh?
That's the one you sent to us.
Yeah,
This is the one that I sent for you guys?
Yeah.
This is the one that I want to send to you guys. Okay, let me see if I can send it to you guys.
Mhm.
Did you want the words to or the sex here and the words here?
Yeah, I grouped the sex as the categorical.
You did?
Yeah, on the bottom. I did it on the
0
bottom.
and 1.
The sex here, right?
Yeah, the grouping.
Why don't you just take that?
Bring sex over to the grouping.
That's weird.
No, go back. Bring sex down to grouping. Bring words.
And then define this one.
Bring the variable over to the other.
We do that here.
Bring 2 of them.
Test variables.
Yeah. You gotta define the variable. No, you didn't define it correctly. Right, define. 0 and 1, not 1 and 2.
Oh, you're so smart.
Oh. So click that, yeah, click that one, and then hit insert, or go to insert, and move to insert.
Thank you.
I don't know, I thought we were supposed to like get credit for this.
Yeah.
Notice that your grouping comes in one column, male, female, whatever. And then all the numbers in the separate column.
Oh, see, because he says.
No, actually, hang on, but. So did you do both of them in one shot?
Yes.
Let me see, let me do it myself, and then we can interpret it. Analyze, compare means, independent, words, years of education, sex. One. So, okay, with regard to number of words, did you go to the top row or bottom row? So you went to bottom row. How about for years of education? Top row. And let's write the conclusion symbolically. For the words, we did a t-test, and degrees of freedom is 189.006 equal to negative 2.75 comma p, which is this number, not the other one, but this number. We reject the null hypothesis. What number should I put in here, guys?
0.01.
I'm sorry?
0.01.
This one?
0. What if we?
0.001?
Yeah. Now, what if we just want to keep 0.05 for the sake of this class? Would we get?
No, learn the right one.
So how do we know which one to write?
Well, I don't know which one is the best one in here. Ideally, I would need to put this. Can I put this one? 1 in 1,000. Well, over there is 7 in 1,000. So this one doesn't fit. Can I put 1 in 1,000? 1 in 100?
Yes.
Yeah. This is better than this one, so I put this one.
Wait, I don't understand.
Yeah, I feel, I don't even know how I'm
Oh,
gonna
yeah.
get that. I get it. It's gonna confuse me like crazy.
Because
This
that 1 in
number is
1,000
what?
would be
7 in
0.01.
1,000, correct? Can you read this? What the number is? 7 in 1,000. Matthew, can you understand that? This is, see, there are 3 digits, that means 1,000. 7 in 1,000 chance that you are wrong when you reject the null hypothesis.
Well, we have to divide that by 2 too, don't we?
No. We're doing 2-tailed tests, so all you need is compare this with the alpha you have in mind.
So couldn't we just write that number down? If we wanted
Not
to?
for this class.
So how do we know?
So this is a reject. Do you agree with me?
Yeah, I understand that part. I just don't know how to figure out what number. That's
Yeah.
what confuses me.
Let me see James, if James wants to.
Well, I was just hopefully try to help them. If you look at the 0.01 and add another 0, it's 10 and 7 is less. or if 05, you can look at it with another zero afterwards to figure out how many in 1,000 and then compare that to the two-tailed number to be able to say it easier.
So, let's put it this way. You want, when you reject the null hypothesis, use one of these three numbers in here. Whichever is the lowest. Whichever is the lowest. If I put 0.05, if I put this one, fine. But can I do this one, which is better? Yeah. So I don't do this, I do this one.
But only one of those three, no other number.
No, usually it is. You don't put 3 zeros, that's too pretentious. Everybody get the point, exaggerating. So the thing is that 0.007 doesn't lend itself to the best one, which is this is the best one. That one is larger than this one. I'm not going to use this one. I cannot use this one. But I can go one step higher and use this one. It's 1 in 100. So you want to use the best of these, one of these three numbers. Whichever is the smallest, yes.
So if we fail to reject, we would just switch the sign, right, to P more?
If you fail to reject the null hypothesis, now remember, if you fail to reject the null hypothesis, you put the alpha that you have in mind. You have failed at this level. So for the fail, you put the real alpha that you have in mind that caused you to fail. That is when you reject and you say that there is an effect, the medication is effective, you want to use the best number that's possible for you to get credit. Remember, this is the amount of error. There's a possibility of you being wrong. Obviously, this is the best one. 1 in 1,000, I might be wrong. Yeah, that's an excellent one. If you cannot use this one, go to this one. Yeah, 1 in 100, I might be wrong. If you cannot use this one, go to this one. 5 in 100, I might be wrong. So how about the education part? You go to the top row or bottom row?
Top.
Top row, this one. Well, this one obviously is very, very small. So my symbolic equation is 198, correct? Top row. And the value of t is negative 7.69, comma, and percentage, this percentage is, we reject, correct? Less than, which of these are best? 0.001. And that number is so small, you want to get credit for it. Say, I might be wrong, 1 in 1,000. I think your textbook says just put 0.05, but that's not a good idea.
Sorry, if that's the lies, you shouldn't.
It's not lot. Actually, put 5 is okay too. You are not wrong.
I know, I understand.
But no one will publish and doesn't get credit for it.
I was just confused because I thought we would just put any number. I didn't know it was only those three, and I didn't know how to determine which number.
Yeah,
But if
no,
it's just
this is-
those,
You compare these three numbers with this, for example, and so, if this is the number, which of those are the best? The middle one. Carlos, go ahead.
Can you explain how t-value describes the relationship between the variables?
Yeah, actually, let's stick to the one sample because this one is denominator is a little. This one is probably can understand it better.
Yeah,
The numerator is always the difference. Well, in this case, actually, let's use this one. I think this is better. We are comparing the two groups. So we are comparing here is the average of words of male and average words of female, that is where the comparison is between the two groups. The averages between the two groups is right here numerator.
Mm-hmm.
And this is the average error. So I think, if I answer it correctly, I think K is the numerator.
Yeah.
And T is based on difference between the two averages.
Yeah. Divided by the error, the standard error.
This is the standard error, average error that might exist.
Okay.
Angel, what do you have in mind?
So, I guess going to what he's saying, what would be the point of having this? How can I ask it? So we're finding the difference.
We want to get the average vocabulary of men in our sample versus the average vocabulary of women in our sample, the two averages, male and female. We want to look at the difference between the two averages. And we get a difference. I want to know whether this difference is large or it is small, basically. So for this one, let's move on to another one. I just sent, go ahead, yes.
Can we take a bathroom break?
Bathroom, fine, okay.
Or a break in general?
Yeah, why don't we take 5 minutes so you can refuel mentally and then come back.